Hello everyone, welcome back. In the last lecture we were looking at vacuum states or vacuum field and then fluctuations. We said that is one of the more intriguing results of quantum theory of light. So in this lecture I just want to quickly introduce what are known as coherent states and talk about the implications. All right. So a coherent state, when we is an analogy, a quantum mechanical analog of a simple monochromatic wave. Okay, so we know monochromatic waves, right? They are the purest form of waves that you can have, and I can construct any object out of various monochromatic waves, right? A sine wave in time is a monochromatic wave in a time domain, and you can have a perfect frequency there. Similarly, in space as well, we talked about plane waves, which are again monochromatic waves. Similarly, we have what are known as coherent states. Coherent states, these are essentially a quantum mechanical analog of monochromatic waves. Okay, we'll slowly see what we mean by this. All right. And we have already seen this quadrature diagram. So you can plot a particular state in in x1 and x2 quadratures, right? So in this regard, I'll define my coherent state as this: alpha equal to x1 plus I x2. Okay, I have x1 and x2 quadratures, and this is my coherent state. And you can see, we already know that this is a dimensionless quantity, right? x1 and x2 are dimensionless, so alpha is dimensionless. Alpha is dimensionless. And I hope you are familiar with this particular symbol that I'm using. This is basically Dirac's bracket notation. When we talked about the transition elements in solids, we talked about the Fermi golden rule, and we said, we mentioned things like F, X, and I, right? This is basically, we said, a matrix element, wherein, essentially you're computing the expectation value of a dipole, right? E times X, the charge times the distance is a dipole, so we can compute X. And this essentially, we said, represents integration over a certain volume of psi of X conjugate times X psi initial dx. Okay, this is the integration. When you integrate this, you got the matrix element. So where this was the ket, and this is the bra. This is the bracket notation of Dirac. When you say ket, essentially you're taking the normal number, like ket will correspond to initial state, bra will correspond to the final state. Okay, so I hope you're familiar with this. If not, just look up Dirac's bracket notation. So now my coherent state is defined as this complex number, okay, dimensionless and complex. Okay, so now let me calculate the magnitude of alpha. So since I have this, let me do alpha square. Since it's a complex number, I can always calculate the magnitude, and that is going to be x1 square plus x2 square. So what is this? Okay, well, this is the magnitude of it. Of my phasor, right? That I'm having. So magnitude square rather. Okay. So what is x1? x1 square. Remember, we defined this in the last or the last before lecture, wherein x1 is going to be equal to epsilon naught v divided by 4h cross omega whole square, whole thing under root e naught, right? So I'll put that in here. So my x1 square plus x2 square is going to be epsilon naught v by 4 h cross omega square we are anyway doing. So epsilon naught square. Okay. For x1 we have a cos square omega t, and for x2 we have a sine square omega t. Correct. So now it turns out that if you look at this, alpha square, or rather if I write alpha, is going to be equal to square root of epsilon naught V by 4 h cross omega E naught. If you have noticed carefully in the previous lectures, whenever we talked about the phasor like this, the length of the phasor, right? The length of the phasor here, we said length is equal to this quantity here, epsilon naught V by 4 h cross omega E naught. So in the, I think in the previous lectures I said, oh, this is going to be proportional to the electric field magnitude, E naught. I didn't go into the coefficient, but clearly this coefficient basically comes from this, it's going to be epsilon naught V 4 h cross omega. All right, so what? Okay, so to physically interpret what this alpha means, or magnitude of the coherent state means, let's go and look back at the energy that is present in an electromagnetic wave, right? In the classical picture, electric E classical, right, energy, classical picture, right? What is that? Is equal to 1 by 4 epsilon naught V E naught square, right? So this is what we have seen, and now we can use that, and then we can quickly see that there are these terms that are there. Okay, let me simplify this by just not talking about. Make my life simple like this way. So alpha square is equal to E square, right? So now it's very clear what it is. So this energy present in the electromagnetic field is going to be equal to alpha square times h cross omega, right? So basically we have these quantities, 1/4 epsilon V and E naught, which are this. So all of that is the classical energy. So that is going to be equal to alpha square times h cross omega. We'll just take this h cross omega here. So that's it. So now we see that this is this. Okay. And we know from our understanding of how we define the energy, if there are n photons, we said that is equal to the total amount of energy in that is going to be n h cross omega. So we see that the magnitude of the phasor, or the length of the phasor, is going to be dependent on the number of photons that are present in the field. Okay, so this means that alpha is going to be the length of phasor is proportional to square root of n bar, the mean number of photons. Okay, so this is my no, so far I have just defined. Okay, we will try to understand what are the implications of it. Okay, so now what is this state? Is it just simply some mathematical abstraction? So well, to understand that, let's look at this. Okay, alpha square is basically n bar, right? So we are given that alpha square is equal to n bar, correct? So now what is delta n? The uncertainty in the number of photons. Well, if your length here is square root of n, we can, and we know the uncertainty here is half. This is uncertainty. This is uncertainty in photon number, right? In my picture of this phasor diagrams, this is uncertainty in phase. There are these two quantities that are there, and we know that there is this minimum uncertainty that is required to be there. We said product of x1 and x2 is greater than or equal to 1/4. So we want to derive an uncertainty in more physical terms. x1 and x2 are related to the field amplitudes. We understand that, and that's how we talked about vacuum fluctuations. But we want to also relate it to the number of photons as well. Okay. So now if my overall uncertainty here is 1/2, and it turns out that the coherent states also have a property that they have minimum uncertainty. Okay. Coherent states have minimum uncertainty. So it will be equal, and the phase will be equal uncertainty. So now because of that, I can write my delta n as simply I have a mean value of alpha, and plus 1/4. Okay, whole square, right? Whole square minus mean value of alpha minus 1/4 whole square. So I'm just looking at the extreme cases. So this is average is alpha, right? The center of the circle. So 1/4 on this side, 1/4 on this side. So I'm trying to just write the radius, the change difference in the length basically. Okay, this constitutes the uncertainty. So now difference in phasor length represents uncertainty. Okay, so what is this quantity now? We can simply expand alpha square plus alpha by 2 plus 1 by 16 minus alpha square plus alpha by 2 minus 1 by 16. These things go out, and what we are left with is going to be equal to alpha, and we know alpha is going to be equal to square root of n bar. Okay, so what we are seeing is coherent states coherent states exhibit minimum uncertainty. And exhibit Phasorian statistics. Right? Because delta n equal to root of n bar. That's why they exhibit Phasorian statistics. So this is my coherent state, right? What else? So there is something called number and phase uncertainty. Just like we had uncertainty relation between x1 and x2, delta x1 into delta x2, we have an uncertainty relation between number and phase. So the length of this, for example, when we defined, okay, I didn't mention it, but essentially when I have this alpha, this I can represent it as in the phasor form. So alpha, I can talk of magnitude of alpha times e per I phi, magnitude and phase of the phasor, right? So there is this phase, and now the phase also exhibits an uncertainty relation. How much is uncertainty? What is uncertainty relation now? So for that, we can look at, let's say we look at the arc length. Arc length, right? In this case, the region of uncertainty subtends an angle at the origin. So then the arc length is going to be equal to the radius times delta phi. The radius, or in this case, is going to be square root of n bar times delta phi. Okay, and that is equal to 1/2 because it's a minimum uncertainty state. So now we know already that delta n is equal to square root of n bar. So I can write delta n delta phi is equal to 1/2 for a coherent state. Okay, for a coherent state. In general, delta n times delta phi is going to be greater than or equal to 1/2. So this is my number phase uncertainty relationship. Number phase uncertainty relationship. What it means is, if I have a large number of photons, what does it imply? What is delta n? All right. If you have a large number, for example, let's look at this. Okay, to understand the physical meaning of it, we said we previously talked about the coherent states, right? And we previously talked about the Phasorian statistics, for a coherent state. So a coherent wave, or will exhibit Phasorian statistics is what we said. And essentially the idea was, you have this number of fluctuations delta n that is equal to square root of n bar, and what happens to the relative fluctuations as the number of photons increases? As n increases, delta n by n bar reduces. Okay, and this implies basically relative fluctuations reduce, and the wave becomes well defined. Right? That's what we saw in the class. I mean, we said that as the number of photons increases, we go into the classical picture, wherein you don't have to worry about the phase uncertainty or fluctuations in the wave, right? But if you are talking about, let's say, okay, in this case, what happens in the context of number phase uncertainty? What happens? So delta n, delta phi is greater than or equal to half is what we said. So as n increases, delta n also increases. It's because you are talking about Poissonian statistics. So that means delta phi reduces. Okay. So as the number of photons increases, the phase becomes well defined. Okay. In contrast, if you talk about the opposite situation, when the number of photons reduce, okay, in the few photon regime, let's say, in few photon regime, delta n is small. This implies delta phi is large. It can even be greater than 2 pi, greater than 2 pi. That means phase is undefined. And it also makes sense in some way, right? Because if you are talking about a single photon regime or a few photons, then what is a phase? It's just particle nature that dominates. I mean, there are problems in actually defining a phase for this sort of scenarios. Okay, and essentially what we are saying is, just like you have a monochromatic wave, if you have a coherent wave, you have this region of uncertainty. That is, you have this phasor plot, and you have a region of uncertainty in the phasor plot, and the magnitude of the phasor is the number of photons, and there is an uncertainty in the phase as well. And those are given by this basic relations delta x into delta x1 into delta x2 has to be, since we said it's a minimum uncertainty state, these things will be, product will be 1 by 4. So what it means is the phasor can be anywhere in this region of uncertainty. That means instead of having a well-defined wave like this, right, we have a situation where your wave is going to be represented by a band here. And the uncertainty in, let's say, the amplitude or phase is constant over time. It doesn't change over time. Okay, that is the physical meaning. That means you have various, let's say various, you can talk of a wave for each of these points, and all of them are averaged, and eventually you get something which is not average. Sorry, if you look at the distribution of all of them, you will see that now the wave is, having a certain amount of uncertainty, and the phase uncertainty is fixed over time. It doesn't change. Okay, the phase uncertainty does not change with time. Okay, so this is my number phase uncertainty that exists. All right. So this is a physical meaning of a coherent state essentially. So you are essentially in a regime where you have few photons, and that means there are fluctuations, and then those fluctuations, the fluctuations in phase remain constant over time. That is the meaning of a coherent state. Okay, it's one of the, the pure state, like like a monochromatic wave, a plane wave. This is a quantum mechanical analog of that. Okay, so just to get an understanding of what this is, we will also we'll also talk about some other states which are not going to be like this. Okay, that's why we want to lay this groundwork. Okay, so now let's try to solve just a small problem. So consider a coherent state alpha, which is with an alpha equal to phi. Okay, the magnitude I should say this is. Okay, this is, well, yeah, the magnitude is phi. There should be a magnitude. Okay, calculate the mean photon number. I mean, this is fairly, it's just trivial. So we said alpha square is equal to the average photon number. So in this case, that is going to be turning out to be 25. The mean photon number is 25. The standard deviation in the photon number, since we are given it's a coherent state, right? Coherent state exhibits Poissonian statistics. This is what we defined. We said it will happen because we showed that as well, right? So now if it exhibits Poissonian statistics, the fluctuations in the number, right? Standard deviation in the photon number is going to be square root of n bar. That is equal to phi. Okay. The third part is the quantum uncertainty in the optical phase. Okay. We said that delta n, delta phi is going to be in the coherent state, it's going to be equal to half. Correct? So delta phi is going to be equal to 1 over 2 into, this is delta n is phi, so 2 into phi, that's equal to 0.1 radians. The phase is basically uncertainty in the phase is about 0.1. Suppose you have, let's say, 10,000 photons, mean number of photons. Okay, just one example. If this is different, suppose n bar is 10,000, large number of photons, then your delta n is going to be equal to 100. So your delta phi is going to be 1 over 200, correct? And that is basically equal to whatever, 0.05, 005, something like this, 0.5005. Yeah, 0.01, so 0.05. Yeah, correct. Okay. So basically you see that as the photon number increases, the uncertainty in the phase reduces. Okay. You might wonder, why do we care about this? Well, it has some very important fundamental implications because, when we can determine the phase accurately, we can, let me not talk about it this week. Next week, I'll talk about an application of this, how these are useful in things like gravitational wave detection and so on. Okay. I'll talk about that next week. I think we will run out of time if I start talking about it now. So what I just want to quickly, close this. This is a coherent state. I want to talk about another type of state which is known as a squeeze state. Okay. And then I'll introduce that and we will discuss the implications in the next week. Okay. So we have already seen this situation wherein we have x1 and x2 quadratures, and then in the phase in this quadrature plot you have at the origin you have this. So this is basically your vacuum state. This is definitely vacuum state. Okay. Now I have another state which I'll call as coherent state. Why is this coherent state? Because delta x1 equal to delta x2 equal to half, right? So therefore the product of x1, x2 is going to be equal to 1/4. So this is the minimum uncertainty that you can have. You have a state which is minimum, that's why it's minimum uncertainty, that's why it's a coherent state. Now, so far whatever we have seen, the region of uncertainty was always a sphere or a circle, a circle. But you can also have an elliptical region of uncertainty. Region of uncertainty can be an ellipse. What does it imply? If the region of uncertainty, now we are actually showing for the vacuum state, but let's say the x2 quadrature is stretched out and then x1 quadrature is becoming smaller. Okay. So here you have a situation where it is in such a way that x1 is less than half and x2 is greater. So what happens when you have this sort of a state? Okay. I mean, we can show that in this case, the uncertainty is never going to be minimum. Delta x1 delta x2 is going to be greater than 1/4. Okay, that is one consequence. But what does it mean if you have such a scenario? Okay, this leads to what are known as squeeze states. We are actually reducing the uncertainty. We are squeezing the uncertainty in one of the axes. Okay, so to understand what this is, let's look at this again. This is again just repeating. Basically, this is coherent state because delta x1 equal to delta x2 equal to half, and delta x1 delta x2 is greater than 1/4 or equal to 1/4. Sorry, not greater than 1/4. Equal to 1/4. Okay. Now, instead of that, at vacuum state, I'm showing another state here wherein you have this phase, the length of the phasor which is there, and that is displaced from the vacuum. This is basically displaced from origin, right? That means it's not a vacuum state. It has a number of photons. Number of photons here is definitely n bar is not equal to 0 here. In this case, n bar equal to 0. Well, this is a coherent state. So that's, it's not vacuum. Yeah. Now, the thing to note is, if you look at the uncertainty, the region of uncertainty is again ellipse, but now it is stretched out in the number direction. In the phase direction, it is reduced. So this we will call as phase squeezed state. Why? Because delta phi is less than half. Okay, and delta n is greater than half. It's not on the circle, it's stretched out. So there's an uncertainty, so this is a phase squeeze state. Similarly, you can have a state where the phase is larger, delta phi is larger and delta n is smaller. So this is amplitude squeeze state. Squeezed state, wherein delta phi is greater than half, delta n is less than half. Okay, so overall delta n, delta phi is going to be greater than half. Sorry, this should be, if I talk about number phase, right? Okay, the number phase uncertainty tells us that it's overall it's equal to half. That's a minimum. It will be greater than half. Okay, so now these are the states that are possible. Okay, so I really we will not discuss the implications in this week. In the next week, when we talk about this, we will revisit and we'll understand what all these mean. Okay, why these squeeze states are important, how do we generate them, how they are useful, and so on. Okay, we will do that next week. But this week, I want to close with this discussion that we introduce this idea of a coherent state, which essentially is a quantum mechanical analog of a classical monochromatic wave, and then that is represented by a ket like this. Essentially, it's a complex number. It's a dimensionless complex number, and basically this is a Dirac bracket notation. If you look at if you take the magnitude of this complex number, you will quickly see that the magnitude of the complex number is going to be equal to square root of n. So if you have a certain number of photons in the field, that square root of that photon number is going to be this length of this phasor, and then we can basically talk about how the energy is, and from that we derived this expression. So we wrote the classical expression for the energy, and then we said, okay, that is going to be n h cross omega, and so this square amplitude of magnitude of alpha should be equal to square root of n. Once we have this, we also introduce the idea of uncertainty. This is a number, and so this is a phase. We said that you can actually express this phasor in terms of a magnitude and a phase. So the phase uncertainty, we derived a relation. We said that there is uncertainty between number and phase. If you know the number of photons accurately, then the phase is unknown. If you have a certain amount of uncertainty in the number, then the phase is phase uncertainty is limited. Okay, that we explained by these examples. We took a case of a large number of photons, delta n is large, so delta phi is very small, and vice versa. And we said the physical representation of this is that if you have a coherent state, it essentially means that you have a state which is like a monochromatic wave, but now there is an uncertainty in the amplitude and the phase uncertainty does not change over time. So it is as close as possible to the classical monochromatic wave. It's not a single line, it's a band, but that band does not exhibit varying phases. Okay, this is a coherent state. And we also quickly introduced the idea of squeeze states, wherein we said that the region of uncertainty need not be a circle, it can be an ellipse. Okay, the ellipse can be squeezed in the direction of the number, right? The length of the phasor is a number, so if the ellipse can be squeezed in that number, or it can be squeezed in the phase direction. So based on that, if it is squeezed in the phase, that means the phase uncertainty is less than the coherent state, then we are calling it phase squeeze state. And if the uncertainty in the number is less than the coherent state, then we are calling it amplitude squeeze state. And we will talk about the implications, how these are useful in the next week. But with that, I would like to stop the discussion for this week. All right. So thank you so much. And please take a little bit of time and review it. And then we will meet you next week. Take care. Bye.